Alright, so this is chapter 13 homework. For the first question, given a bucket, it's full of concrete, it's traveling at a constant speed, that's going to come to a stop. This is going to continue to swing. I'm asked to figure out the maximum horizontal distance that the bucket will swing. So I go ahead and draw my diagrams. Looking for delta x here. Realize that all of the kinetic energy is going to get transferred into potential energy. So I'm just able to solve for h. That height is going to be about 1.55 feet that it's going to swing up. But I'm not asked for the vertical distance, I'm asked for the horizontal distance. So looking at this triangle here, at its maximum height, the distance here is going to be 30 minus the 1.55. So I'm able to use that along with inverse cosine to figure out the angle. I can then use sine with that maximum angle to find that the horizontal distance traveled is going to be about 9.8 or 9.58 feet. For the second question, I've got this cab, basically a truck and trailer setup. It's accelerating up a hill with a 2% grade. I'm given the initial and final velocities. I'm told that it travels 300 meters. I'm given the mass of both the cab and the trailer. I'm asked to find the average force at the wheels for the cab, as well as the average force in the coupling between the cab and the trailer. So the first things I do is draw the triangle for the 2% grade. So that's not the same as 2 degrees. And solve for theta. I then draw my diagrams here, making sure to draw the triangle to be able to convert the weight into the correct x and y axes. By looking at the diagram, I can see that the force of the wheels minus the force of the weight in the x direction is going to be equal to mass times acceleration. When I look at this, I realize I have everything that I need to be able to solve for force of wheels, except for acceleration. Since I don't have time, I use the kinematic equation involving delta x, which is given, and I'm able to find this is the acceleration. I then isolate force of wheels and plug in all of my variables to find that it is about 7.4 kilonewtons of force. To find the force that at the coupling, I start drawing how both of these are related to each other. Then I realize that the force at the coupling is just going to be the mass of the trailer. Okay, essentially all of the force required to push the cab up the hill is already being used before it gets to the trailer. So I just use the same equation, but just put 5400 instead of 1800. And I get around 5.5 kilonewtons. Number 3 is similar to number 2 in the fact that there's several couplings and forces being applied to only one cart. Essentially, the entire train is moving 30 miles per hour when cart A brakes and its wheels lock up. I'm asked to find how long it's going to take for the entire train to stop, as well as the force in each coupling. I'm given its initial velocity and the coefficient of kinetic friction. Go ahead by drawing my diagram, converting the weight into mass, because that's going to be required to find the kinetic energy. Realize the kinetic energy is going to be absorbed by the force of friction. Mu, the normal force, is actually the weight of cart A times the kinetic coefficient of friction, delta x. Go ahead and isolate delta x, plug in the variables, and find out it's about 279 feet. To find the force, I've realized the force at the first coupling between cart A and B, well, that's going to just be the kinetic energy of cart B and C combined. Now, the total amount of force that's going to be created occurs over 279 feet, and I want to find the force per foot, so I just divide this by 279 feet, and I find that the force is around 19,000 pounds. For the next coupling, which is the coupling between cart B and C, it's only going to be, taking the kinetic energy from cart C. So just do 80,000 pounds there. Again, divide by the 279, and we get around 8,500 pounds. For question 4, the sphere is being thrown down with a velocity 5 meters per second. It's attached to a rope that's 2 meters long, and I'm asked to find the angle in which the rope will break, given the maximum tension the rope can withstand is equal to twice the weight of the sphere. I realize that the kinetic energy plus the potential energy is going to be transferred into its final kinetic energy. I'm able to then solve for its final velocity, realizing that h is just going to be the sine of theta times the length of the rope. I then draw this diagram, realizing that I'm wanting to look at how much force is going to be applied to the rope, and that that amount of force is going to be the maximum force of tension minus the normal force of the weight of the sphere, since these are going to be acting in opposite directions. So I create that relationship, and I know that it's going to be equal to mass times the normal acceleration, which is v squared over rho, in this case L. I know that the maximum force of tension is 2 times the weight. By looking at my drawings, I can see that the force acting in the normal direction by the weight is going to be cosine of 90 minus theta, which is equivalent to sine of theta. I'm able to cancel out my masses since they are all the same, multiply the length do some factoring, get the signs on both sides, then divide by Lg minus the 2, and divide by -3, because I end up with -3 sign here. Take the arc sine, and I get that that angle is 14 degrees. Question 5 involves a chairlift that is designed to transport 1,000 skiers per hour. Given the average mass of the skier, as well as the average speed, I'm asked to find the average power required, the required capacity of the motor, given its efficiency, and its overload. Again, I start off by drawing a triangle. I look at the definition of power, which is work divided by time. Work is force times distance, which in this case is mgh. And of course, we're going to be doing this 1,000 times per hour. So I just need to plug in the numbers that I'm given and divide it over 1 hour of time in seconds to get watts, around 57,000 watts, to find the required capacity of the motor if a 300% overload is to be allowed. First off, I did it based off of the wattage that I found, so I wasn't sure exactly what it was asking. I went ahead and did it again with that 300% overload and found that the watts would be about 269 kilowatts. Then by looking at the solution manual, I found that that's the actual answer it wanted. Wasn't sure if it wanted both done separately. For question 6, a collar is guided along a railing. Collar has a spring attached to it. The spring is undeformed when the collar is at C, as it is guided along the railing. The spring stretches. I'm given the mass of the collar as well as the spring constant. I'm asked to find the velocity as it passes through point B as well as point C, and I'm told that the initial velocity while it's at point A is 0. Thinking of how the energy is going to be working out here at point A, I realize its initial kinetic energy is 0. There is going to be some potential energy as the force of weight causes it to accelerate. And there's also going to be some force applied to the spring. So that spring force plus the potential energy is all going to be converted into my final kinetic energy. Go ahead and isolate for the velocity of B here. When I was first trying to solve this, I just did the distance the spring would be stretched at point A, got the wrong answer. I then did the difference the spring was going to be stretched from B to A squared, still got the wrong answer. You gotta square these separately to get it correct, which makes sense. I just didn't realize that at first. But the velocity of B is 2.48 meters per second. To the left, for part B, it's going to start off with some kinetic energy, which I can solve for, given I already know its velocity. It's still going to have some force applied by the spring, And then this time, the force of the weight, or the potential energy, is working in the opposite direction. So that's going to be subtracted. Of course, that's all going to be converted into my final kinetic energy. Go ahead and isolate for velocity. This time I can use just the distance the spring has been stretched at point B, and I get its final velocity is about 1.7 meters per second upwards. Question 7 has a package at the top of a ramp. Given its weight, its initial velocity, the distance it's going to slide, theta, and I'm told that the spring, which I have its constant for, is already being compressed by a cable 50 millimeters. I'm asked to find the additional amount that the spring is going to compress before it brings the package to rest. I realize that the kinetic energy plus the potential energy is going to be absorbed by the spring, which is this: kinetic plus potential equals the spring. Now in this situation, because it's already been compressed, it's going to be the amount that it's originally compressed plus the difference in the compression, which in this situation is delta x of the spring. I go ahead and isolate delta x. I solve for h using sine, plug that in, and I get that delta x is going to equal 0.26 meters, which is pretty close to the solution in the solution manual, but it is slightly different. As I'm explaining this, I'm starting to realize why. I think the actual answer is 0.269 or something like that. But it may be because it's asking for the delta x when the package is brought to rest. First, the spring is going to compress, then it's going to expand and compress and expand until it's brought to equilibrium, which I'm not finding here. I'm not finding the distance at the equilibrium point. I'm finding how far it's going to compress when it's absorbed all the energy. So that's something to look at and think about some more. Question 8 is another truck and trailer question, this time involving a runaway or emergency ramp. I'm given the weight of the truck. I'm told the angle of the ramp, its initial velocity, as well as the secondary velocity after 6 seconds. I'm told it's going to experience a constant deceleration. I'm asked to find the braking force as well as the additional time required for the truck to come to a complete stop. I initially tried solving this using kinetic energy and found that that was leading to a dead end. Looked at the solution manual and then realized, oh yeah, we've kind of changed sections here. We're going to be working with momentum now. Essentially, it's an initial momentum plus the integral of force, and Now the force working in the opposite direction that the truck is traveling, or the opposite direction of the momentum, is going to be the weight in the x direction plus the braking force. Then go ahead and isolate for the braking force by subtracting the initial momentum, dividing by time, subtracting the force in the x direction, and I find that braking force is about 200 or 2,300 pounds. For part B, I have to find the additional time required for the velocity to equal 0. Again, the initial momentum in this situation is going to be the second velocity I'm given, which is 36, minus the integral of the force, which is the same, is going to be equal to the final momentum, which is 0, because that velocity final is going to be equal to 0. T in this case is going to be the additional time, because I'm using V1 here instead of V0, which ends up being 3 seconds. Question 9 involves a collar as well as a weight that are attached via a pulley system. Given the masses of both the collar and the weight, as well as a constant force being applied to the collar, I'm asked to find how long it's going to take, or the time that it's going to take for B to have a velocity of 2.5 meters per second to the left, as well as the tension in the cable at that time. Draw my diagrams. I realize that for A, the tension of force minus the weight is going to equal the mass times acceleration in the upwards direction. Before this, as I do with any pulley problem, I make a relationship here. One rope connected to A, 2 ropes connected to B, so A equals 2B. I go ahead and do the same thing as I did with A for B, relating the forces to the momentum. Again, we're integrating the forces, which is why I get T here. This time, the tension is working in the opposite direction of the force, and there's 2 of them. After getting to this point, I realize that I need to have this in terms of the velocity of B, which can easily be accomplished using this relationship. And that makes this side of the equation a constant, and it will also make this side of this equation a constant as well. So I end up with negative 29.43 T plus the tension is equal to 15, and I also have what I already found earlier. Right here, I'm able to solve for both equations simultaneously. Essentially, what I'm doing is I'm adding the time to time, the tension to tension, and the constant to the constant. I need to multiply it by 2 so that the tensions will cancel out, and I'm able to solve for time that way. I then go ahead and plug in the time to the first equation I had here after isolating for tension, and I find the tension is about 56.8 newtons. Question 10 involves a simple tool used to be able to measure the energy carried by a bullet that shot at an initial velocity into a piece of wood, and the angle theta is measured. And given the mass of the bullet, as well as the wood block, the length of the cord, as well as the maximum angle, I'm asked to determine the initial speed of the bullet, the impulse imparted by the bullet on the block, as well as the force of the cord after the impact. Realize I'm going to be working with some potential energy here. So I want to find out how to calculate H. And essentially the kinetic energy is going to be transferred into potential energy. First time I tried to solve it, I was looking at the initial kinetic energy of just the bullet. I wasn't able to get the correct answer. Apparently that's wrong. In this situation, I need to look at the initial kinetic energy of when the bullet has already entered the block and take those masses combined to be able to get the correct initial velocity. Once I have that initial velocity, I can just use conservation of momentum, knowing that the initial velocity of the block is going to be 0. I can solve for the velocity of the bullet this way. Find that it's almost 780 meters per second. For part B, to find the impulse, well, that's just going to be the momentum of the block plus the impulse, or the integral of the force in terms of time. That's going to equal the momentum of the final momentum of the block. Of course, the velocity of the block is 0. And I plug in the velocity of the block, which is the same as the velocity of the block and the bullet combined, to find the impulse. For C, the normal force is going to be mass times the normal acceleration, and there is not going to be any tangential acceleration, tangential force at this time. Since at this exact moment it's not accelerating. By looking at my diagram, I can see that tension minus weight of both the bullet and the block is going to equal my mass times acceleration of the bullet and the block. The normal acceleration is v squared over rho, or in this case L. I just isolate for t, plug in my variables using the velocity that I already found in the very beginning of part A, and I am able to find that the force of tension is going to be about 19.7 newtons. Question 11 involves conservation of momentum, as well as differences in velocity, similar to those, the little kind of pieces of art or toys that you'd see on offices, except the difference here is there's actually space between the balls. Anyways, given the initial velocity of A just equals B naught, I'm asked to determine the velocities of B and C after or A and B after the first collision, B and C after the second collision, what it's going to be after nth collisions, then given N and E, and I'm asked to solve for the velocity at that time. Looking at conservation of momentum, I'm able to solve for the velocity of A. Looking at the differences in velocity, again I'm able to solve for the velocity of A. And then I do something similar as I did in a previous problem, which was this one. I kind of solve for both simultaneously. I do the same thing right here by adding these two together. I'm able to isolate the velocity of B after the first collision. I'm able to do the same by subtracting them to find the velocity of A. Again, some of these are just going to cancel out in that process. And it kind of solves the problem of having two unknowns. I go ahead and follow the exact same process as I did for part A to find the velocity of C after it is first hit, which is the second total collision. Same thing for the velocity of B at that point. Notice here, since the masses are equivalent, their velocities are going to be the same magnitude, just in opposite directions. I do go ahead and, this is my initial solution here. I'm able to plug in this equation in for the velocity of B after the first collision here. And I end up with this solution, and a pattern can already be distinguished for the nth number of collisions. For part D, I go ahead and just plug in E, which is 0.9, and N, which is 8. Not able to solve for it completely since I'm not given the initial velocity, which would have been the velocity of ball A. For question 12, a ball is connected by a cord. It's struck by a block, has an initial velocity. Given the masses of the block and the ball, I'm asked to find the height that the ball is going to reach, as well as how far the block is going to travel before coming to a stop. I'm given the constant for the kinetic friction, as well as E. It's another question, similar to the other ones. It's going to involve both conservation of momentum, as well as differences in velocity. It is nice that the initial velocity of the ball is going to be 0. That makes things more simple. This side of the equation, for both equations, are just constants. Plug in the masses for the momentum equation, and I am again able to solve both simultaneously. At first, I'm multiplying this by 2 and subtracting. Oh no, I'm just subtracting it. I'm not multiplying it by 2. So I'm just subtracting and isolating for the velocity of the ball after impact. Get 2.4 meters per second. I do the same thing this time by multiplying by 2 and adding to then isolate and find the velocity of the block after impact. Then working on determining h here. I know that the kinetic energy is going to be entirely transferred into potential energy when the ball comes to rest at its maximum point. The masses cancel out, divide by g to get h. And I plug in 2.4 for v, which I had just solved for, to find the maximum height. For the block is going to come to rest when the kinetic energy after impact is all absorbed by the force of friction, which again is mu mgx, with x being the distance traveled, or delta x. Again, I just isolate for x after canceling out the masses, since they are the same, and plug in the velocity of the block after the impact, and find that it's going to be it'll travel about 54.5 millimeters before coming to rest. And that's it. Thank you.